Good afternoon. Today's topic, we will discuss how to tune or to choose the parameters of PID controller using Ziegler Nichols method or ZN method. So basically, as we know, the transfer function for the PID controller can be written in two ways. The first way, Kp plus Ki over S plus Kd times S, right? Or it can be the other, which is Kp times 1. We said in the previous lecture, there is some procedure or tips for designing by trying to trial and error, but this one might not be a sufficient way. And the drawbacks of this one maybe if when you try some values, it might lead to unstable system, or sometimes if you apply it offline or if you apply it online, sometimes this can damage. And in case it goes unstable, it can damage some hardware equipment. So, which is something that we don't want. Therefore, Ziegler Nichols defines in the good way or in an easier way. But the thing about Ziegler Nichols, it will give you the PID controller parameters that can work properly or work fine, but those are not the optimal value, which means the performance will not be the best, but it will give you a good performance, which is, what do I mean by the best? Which means the performance will not be faster, will not save a lot of energy. Sometimes, and maybe it can be slower. It can be, for example, like it has some overshoot, especially when you have PI controller. So I would say it might not give you the best performance possible, but it give you a good performance. That's the point. So the thing, how can I tune the parameters, or what should I do? The first thing, turn off Ki and Kd. So all of them will set to be 0. If Ki and Kd are 0, what's the remaining controller will be what? What do you think? Proportional, which is basically you will turn on Kp only, or Pi or P controller alone. So the first thing, turn off P controller. Turn off, I would say, I and D controller, the remaining only P. Then start from P equals 0, monitor the response, that's the first thing. Then try to increase it step by step. Let's recall the root locus or the Routh-Hurwitz criteria. We said that the gain can be increased until reaching to the points, what's happening? Marginal stable, right? Do you remember that? When we add the gain, the pole location will be shifted until reaching to the gain, it will be marginal stable. So the key, we will try to reach the marginal stable. Try to increase K carefully, step by step, until reaching marginal stable. So here, how can I know in marginal, we have reached the marginal stable, especially if we don't know what the system is, or if we don't know the characteristic, or when we are doing online, you will monitor the outputs until sustained oscillation occurred. What does it mean, sustained oscillation? Until continuous oscillation happening. If, for example, the system is stable, it will be decaying. Even if there is oscillation, it will be decaying, right? So our target is keep increasing the K until reaching this situation. Once we reach this, which is continuous oscillation, this means the system is marginal stable. Then stop here. Once we have reached this point, we will say the K that we have reached to be marginal stable, we call it K critical. The next thing, we need to determine the period. The oscillation period, look at the peak value and measure the time between peak to peak. This we call it PCR. This is the period, the critical period. Again, K critical is associated with what? Associated with the gain to reach the marginal stable. Then P critical is the time period for this, what's called for this oscillation. If you increase K more than K critical, what's happening to the system? Will be unstable, exactly. So that's the point. We will reach that period. How about if, for example, if we keep increasing K, but there is no oscillation happening? increase K, nothing happened. What should I do? In this situation, you cannot use Ziegler Nichols. Some systems, you can keep increasing K, but it will not it will not be unstable at all. Then in this situation, Ziegler Nichols will, I would say, will fail or will be insufficient to do this. Then you need to apply another methods, which is not our scope now. But I would say you cannot apply Ziegler Nichols for every system, for just special cases, or I would say for fewer range, not for all of them. So step number one, turn off I, turn off D, only P alone, then keep increasing P, Kp from 0 until reaching oscillation, which is reaching marginal stable. Then record K critical, record the PCR, which is the critical point. Then after that, what should I do? Use this table, and that's it. You need to memorize this table. Memorize it. Now, it depends on your controller. Are you using P controller? If you are using P controller, therefore, Kp will be 0.5 times K critical. If you are using Pi, it will be 0.45 K critical, and Ki will be 1.2 Kp over PCR. When you are using PID, then it will be 0.6 K critical, 2 Kp divided by PCR, and Kd will be Kp times PCR divided by 8. So you need to memorize all of this still. So how we derive it, it's not our scope. Now I would say just like use this result. Again, the good thing about it, turn off I, turn off D, keep increasing Kp until reaching marginal stable, record what's K critical, record the period, then use this table, problem done. You will get a good shape, a good performance, then everything can be achieved. The good thing about it, this is called online tuning. What does it mean? Online tuning. Do I need to know the information about what's the transfer function of the system? No. I will not use the transfer function. That's a great thing. The other thing, do I need to check the stability, the other thing? No. So I'm just applying this, that's fine. So the good thing about Ziegler Nichols, you have a box, that system, that you don't know what's inside, but you can apply PID controller, then you will do the closed loop. If your target is step function, for example, then the PID, you can use Ziegler Nichols to find the tune the parameters, and that's it. Without the need to know what's inside the system. Again, this is called online tuning, which means you can do it in hardware. You have a black box. Excuse me. So here, we don't know the PID, or we don't know what's inside the system, but we can do it. Again, this we call it online tuning, which means we can do it in hardware, in hardware application. You have your device, then you can do it. Okay? This table is associated with this formula or this type of transfer function of the PID controller. How about if we have the other type? You remember there's two types of the transfer function. This is the first one, and this is the second one, right? When you are using the second one, here is the table. So this is another table. You have the choice to memorize these two tables or just memorize one. You can derive the others by doing the relationship between Kp, Ki, and Ti, Td. Okay, so this is the same thing, but using the different notation or different transfer function. This is called practical transfer function, the other one, which is the theoretical transfer function for the PID controller. Okay, all good? Clear? Keep in mind here, they are calling PCR sometimes in this as TCR, TC. Just for your information, so if you don't know what's TC, it's the same as PCR, P critical, but just in different notation. Okay, does this make sense? So the overall about Ziegler Nichols and online, this is online tuning by achieving this table. Online Ziegler Nichols and offline Ziegler Nichols. What's the difference between them? Online, again, Ziegler Nichols, it's applied in the lab. So what you're doing basically, make this 0 and this 0, the only remaining is the P controller. Here, this summarizing this stuff. So this is a P controller. Then after that, we will select a small value of K. Try to increase it step by step. Keep increasing it and monitor what's the outputs. If we realize the outputs like this, decay with time, then this is not T critical. That's not K critical. Here, if K less than K critical, here, if K equals K critical, then the response, if K larger than K critical, it will be what? Unstable. You see? Our target is to get this situation. Don't make it too much high, K critical. Just try to increase step by step and observe. The next thing after that, after we do change it, keep increasing Kc until observing increasing Kc until sustained oscillation, which means you will reach the marginal stable. Then you will monitor or measure T critical, or sometimes we call another notation as PCR, whatever you want to call it, TC or PCR, the same. Some textbook call it TC, other textbook call it PCR. Okay. Then the next thing also to calculate K critical, K equal K critical. After that, when you record the value, measure KTC, then you will apply this table. Then you will do the Ziegler Nichols. Again, this is called offline. I'm sorry, I would say online tuning. And in control system lab, there is experiment number 10. It will be Ziegler Nichols. So this is the last experiment in the control lab. You will apply this in hardware. Then you can apply it in real life. How can you do the closed loop system? Then you'll look at the outputs. That's one of the experiments in our curriculum here in the lab. So definitely you remember this. Now the second half, which is offline tuning. What does offline mean? Online, you will do it on site, do it in the lab. Offline, you will do it before going to the lab. Online tuning, the advantage of the online, if you don't know what's the characteristic of the system, if you don't know what's the transfer function, everything is all right, you can do it. However, offline, you need to know the internal parameters of the system, which means you need to know the transfer function. You need to know the feedback. So offline requires information about the system. However, again, online, you don't need to have information about it. So here's the one. Consider this closed loop system showing in this block. Here is the characteristic equation, we don't know it, and we'd like to apply PID controller. So the question is, find the optimal value, or I'll say, find the values of Kc, Td, Ti using Ziegler Nichols. The second one, test the stability. This is very important example for the exam, the final exam. Okay, definitely you will see it in the test. Let's apply Ziegler Nichols. According to Ziegler Nichols, we said that to the procedure, we will remove Td and remove this term, which means we will assume G of S will be Kc alone, or Kp, whatever you want to call it. Okay, so substitutes Kc here, and instead of the long expression, this one, and instead of this one, it will be only Kc. When you do it with Kc, our target is to get K critical, right? Which means we need to make the system marginal stable. How to make the system marginal stable? Find the characteristic equation and do the stability test, which is Rath-Hurwitz. So the first thing, we say this is Kc, then the characteristic equation will be 1 plus Kc, I would say here is G, here is Gm, Kc times G times Gm equals 0. So make the product KC times 1 times this part times this part. It will be 1 plus KC over 1 to S plus 1 square S plus 1. Okay, did you get it? After that, multiply both terms by this one. Then this yields this characteristic equation. Now the thing which is, we need to do the Rutherford stability to make sure to determine when is the system will be marginal stable. So how can I do Rutherford? This is S cubic, S square, S power 0. Then let's use here is 4, 8, 5, 1 plus Kc, right? So what's gonna the term here? What's gonna be 4 times 1 plus Kc, okay? Minus, it is negative. 4 times 1 plus Kc, okay? Minus will be plus 40, okay? Divided by 8. Then this element, let me make it this way, 5, 1 plus Kc. This element, since these two are zeros, therefore it will be 0. How about this element? When we divide it, it will be 1 plus K. So our target is to make sure K, every time K is positive. So if we look at 1 plus K larger than 0, or less than 0, or make it equal to 0 at marginal stable equal to 0. So K equal -1, we don't want the negative number. The next thing is to look at -4 plus 1 plus 1K. 1 plus Kc plus 40 divided by 8 equals 0. Why I make it 0? Because 0 is the neutral. It's the time when it's switched from positive to negative or negative to positive. So to get the marginal stable. So make this term equal to 0. The same thing like I said. Then it will be moved to the other side. It will be 4, 1 plus Kc equals, divided by 8, equals to 40. So this will be 1, here will be 2. 1 plus Kc. Am I right? Okay, I think 4, 8, 40 equal 4, 1 plus Kc. That's the thing. Divide by 4, it will be 10 equal 1 plus Kc. Therefore, Kc will be 9, right? So this is the maximum value. If Kc larger than 9, it will be what? Unstable. So I would say, if the question says check stability, you will say if Kc is bounded between 0 to 9, this is stable range. If Kc equals 9, this is marginal stable. If Kc larger than 9, it will be what? Unstable. So the point is we determined Kc. This is, we call it offline. We just calculated Kc. The next thing is to calculate the period. How to calculate the period? Basically, look at the characteristic equation. Here, the original characteristic equation. Here we have, let me see, 8s squared plus 1 plus Kc. Oh, let me see. Where is it? Then 8s squared plus 10 equals 0. Therefore, we will calculate, try to find s. But where did we bring 8s squared plus 1 plus Kc? We will look at the element associated with this row. Okay, this one, since here we say s power 4, s cubic, I'm sorry, s squared, s power 1, s power 0. So the thing here, we will look at the second row here. Then this is 8 associated with s squared, 1 plus k associated with s power 0. So we'll look at the column or the row above this one, because we already did the criteria here. Look at the row above it, which is this one. Then it will be 8s squared plus 1 plus Kc equals 0. Then substitute Kc as 9. It will be 8s squared plus 10, 9 plus 1, 10 equals 0. Therefore, s squared will be -10 over 8. S will be plus minus j, because square root of -1, root of 10 over 8. And here we just calculated it as 1.11. Well, 1 point plus minus 1.11 J. This is S, and we know S as a complex number in S-plane mode, which is sigma plus J omega plus minus J omega. Sigma here equals 0, therefore J omega equals 1 J 1.11. Therefore, omega equal 1.11. And what we know about omega? Omega equal 2 pi times F, or 2 pi over the period, T critical. So we said 1.11 equals 2 pi over TC. Then TC will be 2 pi divided by 111. Then it will be 5.66. As a result, we can say K critical 5.56, T critical, or sometimes we call it P critical. It will be 5.66 seconds. Now, since we did this, we can apply the table to do what's called the Ziegler Nichols. I'm sorry, yeah, you're right. Thank you. Okay, critical, it is 9. That's great. Thank you. Now we can use Ziegler Nichols based on whatever controller I need to do. So if we need to use PID controller, go back to the table, and the PID controller, the question asks us this format, then 0.6 Kmax, TC over 2, TC over 8. So we will say that here, TC over 2, TC over 8, 0.6 times Kmax. 5.4, 2.83, 0.707. Then substitute them here. This yields this transfer function. Okay, does this make sense? Now we are done with the first step. Any question? Yes.
How did you know which floor the question is?
Let's look at it. It's already been written here. And keep in mind that the question asks us PID controller. How about if ask you P controller or PI? Do you know how to find it? Just use the table. The same procedure, but the last step. The next thing, don't forget the next step, which is test the stability with the new PI, with the controller. We already did the stability here, but now with the controller, let's check. To test the stability, here is the new controller. Then do the characteristic equation. This one times this one times this one. 1 plus, here is, I would say, G controller, G feedback, or I would say like this is H. So we can say 1 plus G controller, G and H equals 0. Substitute them. This is G controller. This is GH. Okay? Equals 0. Then this yields to this one. Then how can I find the stability? If it is short, you can find the roots. I mean, if it's not power 4, if it's power 2, you can find the poles and that's it. But since it's fourth order, then do Routh-Hurwitz. Then when we do with Routh-Hurwitz, it will be 4, 8, 8.8, 6.377, 1.9. Then after that, to find the determinant, it will be 5.61. Here is 1.9, then 3.66, 1.9. This yield, since all of them are positive, therefore it is stable. Okay, this is a summing example. You're doing Routh-Hurwitz, you're doing the stability, then doing the design, and the same thing, you're doing the closed loop stuff and the other thing. Okay, this is the last example. It's supposed to be homework, but I'm not willing to give it you because you already done with this semester. This is very important example. Consider the closed loop in this block diagram, design the PID controller offline Ziegler Nichols. Here, the question tell you use this format. Okay, if you ask it which format should I use, then use this one because the question says use this one. So design the PID controller, then do the system stability. It's very similar to the previous example, with different maybe answers. So here we have exponential. Yeah, it's just, I mean, just deal with it. Deal with exponential. That's fine. There's no problem with that. The justification is the timesheet.